Cool. All right, we can get started. Thanks everybody for joining another session of ML Performance Reading Group. Today's a little bit of a different paper. It's not so much on like the systems layer or kernel layer or anything like that. More in the kind of model architecture aspect of improving um, model performance. In that the time complexity of some um, famously heavyweight computations that are occurring in transformer models can be improved with some clever algorithmic and mathematical tricks, which I wanted to more deeply understand. So for context, we're looking at the Kimi linear paper, which proposed this kind of like subquadratic attention mechanism, kind of builds on gated delta net and other previous linear attention works. I'm just going to talk about the Kimi delta attention today, not the whole paper and the whole model architecture. But the TLDR here is like the motivation why we're looking at this one is that it's the first, well, a couple things. One, it achieves, apparently 6x decoding speed up for 1 mil context when at inference time, and then also reduces KV cache usage by 75% because they're using global attention only on 1 out of every 4 layers, transformer blocks. So 3 out of every 4 transformer blocks don't have a KV cache, basically. So great memory, capacity improvements there. And interestingly, there's been a lot of linear attention papers in the past, but this is the first one that I've seen that claims to outperform just full multi-head latent attention as their baseline. So from like DeepSeek. And I thought that was quite interesting. It either matches or outperforms in some evals, which they kind of show here. You can see Kimi linear on the 128K context length eval here, and then also Kimi linear right here for the 4K MMLU eval here. And then you can see the decoding throughput increase with up to 6.3x when hitting 1 mil context length. So that's kind of the motivation. Very good performance, and both on the actual like execution sort of performance, and then also on the like evaluation performance. So with that, I'm going to open up some slides from Songlin Yang, who is from MIT, PhD student there, who's worked on linear attention a lot. She worked on like gated delta net. And I started, as you can see, working on my own slides here, but then I found hers during my research, and they had everything that I was going to write. So might as well just use these. So yeah, just credit to her. I'm also going to show a couple snippets from a blog post she wrote that was really good. So with that, I will get started. There's a lot of slides here, so I'm going to skip through some and just try to use time efficiently here. But to set the stage, everyone knows some issues with transformers, quadratic time complexity for the attention mechanism with respect to our sequence length, which can get quite large. So that's something that a lot of researchers have been looking at trying to improve. And then at inference time, we have linear memory complexity because we need the KV cache, and we're storing key and value projections for each token. And so, the longer our sequence length gets, the more memory we're going to need to store the KV cache. And this is famously a problem and a burden during inference. So let's, starting from kind of first principles here, revisit our old friend, the RNN, which does not have some of these problems. It has different problems. During inference, we do not need to store the KV cache because it just has a hidden state that it updates at each time step or at each token during the autoregressive decoding, and basically you don't have to actually store a key and a value for every single prior token in the context. So great for memory, constant memory. Training has linear complexity. However, they're not parallelizable because of the sequential nature of the design, which is a huge problem because we want to take advantage of our massively parallel processors like GPUs, TPUs in order to train things more quickly. So that's kind of why we aren't using just pure RNNs. But there's been things kind of like it doesn't show RWKV here, but various kind of linear attention models, gated linear RNNs, state space models, and then the family we're looking at today is linear attention, which is its own little subspace of the research work on improving things, hopefully beyond what a vanilla RNN can offer us, but also solving some of the issues that transformers have. And the reason we're looking at Kimi today, or Kimi linear, these hybrid models, like I mentioned earlier, they have a mix of full global attention and some of these subquadratic attention mechanisms. Basically, researchers are finding that you don't necessarily need full global attention on every single transformer block, and you can still ensure information percolation across the entire sequence with, an occasional global attention, but it's not necessarily um, necessary to get similar evals using more efficient mechanisms in most layers. So now we can look at linear attention. So for context, I personally had never really dived into linear attention before. So I'm going to share what I've learned just recently about it. Please feel free, anybody jump in, correct me if I say something wrong. It's hard for me to monitor the Discord chat while I'm showing this, so just pipe up. It's totally fine. So yeah, this is just a brief setting the stage. If you just remember, softmax attention, just our standard attention we're all familiar with, right? We do softmax around our QK transpose with the causal mask before then, applying that kind of like value projection matrix to get kind of like an aggregated update based on the affinity scores between our queries and our keys. And that's for training, but then for inference, we still do also, softmax. This is for a single token, what that would look like. So what is linear attention? How's it different than this? It's literally just removing the softmax, at least in the most vanilla form, which was very surprising to me because I'm like, well, now this is just like a chain of linear operators. Doesn't seem very expressive. Why would we do this? It seems like a weird thing to do. And basically, there's, well, a variety of reasons, but the first important one is that it unlocks an important property called linearity, where now, since we just have these like linear operators here, we can take advantage of things like associativity, meaning that we can rearrange things and regroup like parentheses and whatnot in a way that can be favorable to us in model architecture design of this kind of like new parallel attention mechanism we're looking at. So basically here, this is just for one output token, right? And so Q transpose K is just an inner product between two vectors. So this is a scalar. You can see here it's part of just real number domain. And so we can, get the same scalar by doing K transpose Q. And then we can also, by associativity, regroup the parentheses, right? So now what we see here is when we regroup these parentheses, we have an outer product here between V and K transpose, right? Row vector and column vector. And so this produces a D by D matrix instead of a scalar. And this is key, and this will basically, be something that we accumulate, and you can see the accumulation here in the summation, accumulate and kind of use later as a sort of compressed representation of like a KV cache where we are storing this kind of mapping from keys to values, like an associative mapping in keys to values in this more compressed state. Rather than a full KV cache, we have this transformation that ideally, given a Q, should produce some, we should be able to quote unquote query it, and it should map us to some value. And just as a simple example of this, if you look at the equation here, if K and Q are just unit length vectors, we'd have K transpose Q. And if they're just unit length vectors, I guess this would be if they're orthogonal, or I might be wrong about that. But basically, in an ideal world with unit length vectors, this would produce just one, and we would get out our value, right? So that's kind of, a simple example of how this should work in theory, to have this kind of compressed mapping from Q to V. So now that we've determined why, we've shown why we want to kind of do this, use associativity to group things this way, and then kind of use this outer product accumulation as a state matrix sort of. How is it used in linear attention? Basically, we will continually at every time step update our S matrix, right? This D by D matrix with the new outer product of the new key and value for this next token, right? And we will just, in this vanilla form, we will continually be updating the state matrix with the next outer product, just naively just adding, right? And to produce an output projection for a given query token, we can simply quote unquote query like I showed here, and it should hopefully map us from a Q to a V if the K and Q for the Q and the K that are most similar, with some quote unquote lookup error between for any other keys that it is like a little similar to or not similar to at all. And I can show briefly, I have a slide that just kind of shows this, where you can see for a given vector that we're querying the S state matrix with, there will be, this, if you look at the math between the matrix and the vector multiplication, we'll do this summation here and we'll see, basically it's, we'll get out the, in the ideal world, say V of J, we map almost exactly K of J to the Q, because remember this S, or sorry, there's no Q here. K is very similar to a Q, right? For a Q, we're hoping that, we're going to have a high, like a large dot product or cosine similarity with some K. In this case, they're just using K, but this could also be a Q. So yeah, but anyways, V of J will be the one where we're actually mapping to with the high similarity metric. And then the rest, where I does not equal J, like other tokens basically, we will have some amount of lookup error, right? Where KT and KJ, or sorry, KI transpose and KJ, this inner product here, will be some non-zero value. Ideally, they should be zero, right? We should get zero lookup error and only map to exactly V of J. But in practice, of course, that's not going to be true. This will only be true, as I mentioned here, is if all these keys are orthogonal, which is, as they say here, a fundamental limitation. In a d-dimensional space, you can only have at most d orthogonal vectors. So there'll be some amount of retrieval error. So this is kind of one of the limitations here, but just going back to this, that's kind of the idea here, is that we can simply, the benefit though of this is there'll be some amount of retrieval error, but Q, this matrix vector product, the time complexity here is much more favorable. We are not having to go through all prior tokens in the entire sequence computing KQ transpose. This is a simple d by d by a d by 1 column vector, right? So in terms of cost to compute that, it's just much more favorable. There's still challenges in training though. For training, because this is computing a single output, like you can picture like during the decoding phase, as we're auto-regressively decoding, updating the state for each token, producing the output for each token. But for training, we still have something that is quadratic with respect to sequence length, right? QK transpose, we have to mask, causal mask, and then get a projection using our WV to get our output projections for the given sequence of tokens. That's the challenges in training with the parallel form, obviously, where we talked about quadratic. The challenges with the recurrent form are basically these rank 1 outer product updates that we talked about, right? V and K transpose. The GPU tensor cores are not going to be used for this, at least if this naive like single vector outer product, because basically the MMA PTX instructions to actually utilize the tensor cores, the operands must be at least like 16 by 16. So if you just have a vector, it's not going to be used. You lose CUDA cores, and so our flops throughput is significantly lower doing this. So we basically, the challenges here to how do we do this more efficiently in a way that utilizes tensor cores, and that's something that we're going to look at later. So they've looked at something called chunkwise parallel form, where basically you divide up the sequence length into chunks of size C, right? And then what does this do? Well, key thing here is that they know it's not an approximation. Like many linear attention mechanisms, they have some approximation. This is not an approximation. This is just a strategy for computation that helps parallelize and take advantage of our, later we'll see how it takes advantage of tensor cores, but one step at a time. So basically this form is only going to compute the last hidden state per chunk, and it's going to share that hidden state across chunks. But within a chunk, we'll still have to use the parallel form we talked about. So we have some diagrams here. First, just a little notation. You can see this bracketed I subscript is the this hidden state for the ith chunk, the last one. So that should contain all of the key value updates that have been added to the hidden state within that chunk. And then Q of I, K of I, V of I, these are all just the queries, keys, values, etc. for that chunk. So you can kind of see here what this will look like. The hidden state, the last hidden state for chunk T here will be, or I guess this is like say T plus 1, will be the hidden state from the previous one, just T, plus all of the key value mapping updates that we want to add to that hidden state. And we'll still just have a D by D matrix. And this is, the time complexity of this is not high. It's just D squared per chunk, because this is a, we're computing a D by D matrix here, and so that's going to be D squared. But per sequence, or per the entire sequence, we're doing that, up to L times. So still, this is much more favorable than L squared, because L might be like 1,000,000, whereas D might be, say, like 4096 or something. So much more favorable for that term to be quadratic there. Finally, if we look at the parallel computation now, as I mentioned before, the intra-chunk portion here is still, we're doing a full QK transpose, which is quadratic, but instead of with quadratic respect to the sequence length, the full sequence length, it's quadratic with respect to the chunk size, C squared, which is much more favorable, because the chunk size will usually be set to something much, much smaller, like 64 or 256, okay? And this is basically amortized, so if you're just adding together a bunch of, chunk squared, and this one's chunk squared, and they're all parallelized, you get something much, much faster than a full L squared computation, okay? So we can see here the output projections for a given chunk of tokens is going to be the queries for those tokens, right? Stacked query vectors for those tokens, mappable with our hidden state, plus then the normal like kind of quadratic attention within the chunk, quadratic with respect to the chunk size, right? So then we get this term for our computational complexity, which, as you can see, does not contain L squared, which is the key property that we were looking for here. And yeah, like I just mentioned, the C is typically set to 64, 128, 256, something much smaller than your full sequence length. And so we achieve subquadratic complexity, but we're not done yet. This is the kind of naive linear attention with chunk-wise parallel computation. There are, problems with this. So we'll look into, discuss briefly some of the more latest research as we build to Kimi delta attention here. This is, they're just talking about some kernels they wrote that are sort of I/O aware, sort of like flash attention, to get some runtime improvement here. And moving on, some brief kind of intermediate milestones that were looked into and published before Kimi delta attention. First, just to set the stage on what are the next problems to solve with this linear attention we just looked at. Well, it's not very expressive. As I mentioned before, moving to softmax and just having linear operators like this, naively just accumulating the key value mappings like this into the hidden state. It's, for one, weights all updates equally. We're just naively summing without any kind of more intelligent weighting. And in language modeling, the most recent tokens are much more important for predicting the next token than tokens that were like 500,000 ago. So it doesn't account for that at all. It doesn't have any mechanism to enforce this kind of weighting. So some people have tried certain things. One is just like a scalar constant decay factor to our hidden state that is applied with every single update as we go through the tokens, right? to kind of start decaying the weight of the previous mappings of K and V that were added, and before we add the new ones. So there'll be some recency bias, right? Especially as older tokens are repeatedly incurring this decay factor, say 0.9 every time. So there's some papers on that. People went a bit further and they started saying, okay, instead of a constant decay factor, why don't we try a data-dependent decay factor that is computed for every x of t, every token. We have a data-dependent decay term. Okay, and this enables quote unquote like more dynamic control of the retention of our hidden state, or the mappings from keys to values, right? So some forms of this are in things like Mamba 2, MLSTM, in fairly recent papers, 2024. I guess that's like a long time ago now in some ways, but yeah, and the way this would be implemented in practice in a parallel form is rather than just have a mask here, a regular causal mask, you would have the 0 for future tokens, 1 for the current token, and then for all previous tokens, you would have the cumulative product of the decay terms, right? So that's how that would be implemented in practice. And then finally, some people looked at more fine-grained decay, using basically this outer product here between like beta and alpha vectors to get a D by D matrix. And so you have this kind of like, you have this, S is also D by D, so you have like a single, you have a term for every single value in S of t, and you can do a matrix multiplication here. And yeah, some things like RWKV, I've looked at this. But still more work to be done. As you notice, none of these have really taken over the world yet, so there clearly is something, is still missing. More expressive update rules, basically. So this is kind of interesting. They set the stage for this by talking about the fast weight programming perspective, which I thought was a cool way to look at this. Basically, what this means is that our regular WQ, WK, WV projection matrices are quote-unquote slow weights that are shared across all time steps for the full sequence and are only updated once, by gradient descent per training step, versus the S of t, state matrix here is more like a fast weight matrix that is updated on every single state, because it's not really like a traditional weight in the sense that it has it's like model parameters that are updated via gradient descent, but it is still a projection that we are using to compute our outputs of a given layer, right? So it's sort of like a quote-unquote fast weight update. It's a weight that is like updated fast, at every time step. And they then start looking at the update rule for this fast weight, right? From getting from S of t minus 1 to S of t. We've been looking at something, the kind of simple version of the update rule called the Hebbian update rule. But now people started looking at something called the delta rule, which gets its name from basically, instead of just naively adding the key value mapping here to our state matrix every time, even with some decay factor, they instead take into account the current prediction or value that we project to from if we query the state matrix with a given key, and what it is quote unquote supposed to map to, like the actual value for that token, the value vector for that token. So it's kind of taking into account the delta, so to speak, right, between what we currently get when we query it and what we quote unquote should get. And then we take into account some decay factor, right? And then I have a small slide on this. This is also from Songlin's blog, but I just thought she put it in some good words here, saying that it basically applies this error correction principle to linear attention. So instead of simply accumulating the VK transpose outer product to naively accumulate these updates from these mappings, it updates the state based on the prediction errors, right? Where S of t minus 1 matrix vector product with this K of t here, like I mentioned, is our current prediction, and V is the target. So this is the quote-unquote delta rule, right? And we're getting close now. Kimi delta attention, right? We're on our way. Um, so yeah, going back to the slides here, if we're looking at like what the actual objective is here and why the delta rule might be better than like the Hebbian update rule, um, we want when we query S with the column vector KT, we would like it to map to VT, right? And sort of like as this compressed representation of the KV cache, sort of. And there's two ways. So basically, there's um, two ways that you can potentially, maximize the alignment between your predicted projection and the value that you actually quote unquote want. One is by minimizing the angle between them, and one is by enlarging the magnitude of this vector that you get from the projection. Um, and basically what we want is, and they communicate this with this quote unquote like learning objective of the like minimizing this the lot like a fake it's not a real loss function, which I thought was kind of confusing. This is an obvious, it's not a real loss function that we're like literally optimizing and doing backprop with. This is just saying it's like an ad hoc sort of explanation of what we're trying to achieve here in our fast weight update. The dot product, like the similarity between these vectors, should be um, maximized so that the loss when we add this negative are minimized, right? And like I mentioned, two ways to do that: minimize the angle or maximize the magnitude. And the worrying thing is that there's nothing enforcing the norm of this projected SFT KFT. Um, we're not penalizing a large norm here. So it might just learn to make this as large as possible rather than actually minimizing the angle between them and having them kind of quote unquote point in the same direction in vector space. Which is what we prefer, because if we have large magnitudes of this vector, this famously can produce numerical instability during training. Anytime we start getting like crazy norms on gradients or anything you probably have seen in your work before, things can become unstable during training. So what they do is they claim with this delta rule that it's more akin to minimizing the L2 norm between the projection ST-KT and VT. So that way it does kind of penalize the magnitude and enforces or kind of coaxes the model towards minimizing the angle between the current prediction and what we want to map it to, right? And supposedly, according to their research, this also helps with better associative recall, in context associative recall. So like if I had this prompt mapping letters to numbers, and then I asked what are the, what is A map to, what is C, and so on. Apparently DeltaNet with this delta update rule performs better across all model dimensions tested than other linear. These aren't all linear attention models, but models with subquadratic attention mechanisms, like Mamba, GLA, RWKV, etc. So you know, at the time this was published, claims to be the best, right? This I won't spend much time on. It's just saying that, you know, with a data-dependent non-diagonal transition matrice, that's the update rule, transitioning from one state to the next, we can achieve a higher, a more expressive computational complexity domain called NC1 that is, you know, able to handle more tasks that require more expressivity to accurately model, like chess encoding, than a simple vanilla transformer, as I believe what the slide is trying to convey here. So now what we look at here is the my favorite part, basically, the actual update rule, which is now we're actually approaching something very similar to the Kimi Delta Net attention paper. So I might switch back and forth between the paper and the slides now. But basically, the update rule that they've chosen to implement here looks a bit different, right? But this is the transition matrix that we're applying to the previous hidden state at every new time step before we add the new key value mapping for that token, right? And what this resembles is something called a householder reflector matrix, that if beta is equal to 2, it would be a householder reflector, which basically is something that can be used to reflect a vector over some hyperplane. So by replacing the 2 with a beta, it's quote unquote generalized. So you can say if the model set it to 1, it would just kind of like squash the vector rather than reflecting it over the hyperplane. Or you could have some arbitrary value here that determines, how much to squash or reflect the vector. And so what this is basically doing is quote unquote erasing the component of s of t minus 1 that is parallel with this k of t, right? The key that we are trying to erase a previous mapping for, sort of, before we update the new one. We update with this new information here, right? Rather than just mindlessly, shoving them all in, okay? And I actually have a quick slide on this because I looked at this, and for me, I was not clear. I just wanted to understand more deeply, like, how does this k by k transpose, like, how does this actually implement? Like, I understand conceptually it's supposed to erase some of the information from the previous mapping before we update with this one, but how does it actually implement that? And so Gemini gave me a little example here that helped me understand. I thought maybe others would find useful as well. If we look at the kind of a simplified or a simple case of this exact matrix, right, where beta is just equal to 1 and k of t is just a unit vector, then basically, if we go through the math here, we have our S matrix times this erasure matrix, right, the identity minus KK transpose. First, just distribute the S, and this will be what we define as the cleaned matrix, right, we've had this mapping removed. And now, let's say that same key comes along again, and we probe the matrix. We do the matrix vector product here. Well, what happens? Well, let's substitute in our S clean, and when we use the associative property now, because these are just linear operators, and do K transpose K, these are unit vectors, so that just equals 1, and lo and behold, S of K minus S of K is equal to 0. So we have, in effect, erased the prior mapping. And so obviously this is a kind of simplified case where beta is 1 and k is a unit vector, but you can see kind of how the math is attempting to implement this now. So yeah, going back to the main slides here, we're almost at the end. Now let's look at how this actually looks when we unroll this kind of. So here's the transition matrix, right? The householder transition matrix, and here's the new key value mapping we're trying to add. So what does this actually look like? Well, it looks like this. It's like a nested loop, sort of. So this is pretty gnarly, but there's a reason we're doing this, which we'll see later. Basically, for every token, right? So for I through T, so for every token I, we are going to compute the key value mapping that we want to add to our state matrix, right? This is for I. Then starting from I plus 1, going to T, so for all future tokens, we are going to compute the cumulative product of the householder transition matrices, right? And then multiply that by our token here. So we're basically saying, and then we're gonna add that, accumulate that into finally our state matrix. So we're basically saying, for this token, compute the mapping and apply all the decay or erasure that would have happened at each time step up to the current token we're at, T. Apply that to the original mapping we had before accumulating it finally into our state matrix, right? So that is kind of what the unrolled form looks like, so to speak. And I have a slide on this. It's just kind of the same thing, though. I think maybe I should remove this slide. But oh no, it's actually good, because now here's the first time we are going to start mapping the delta net equations to Kimi delta and seeing the difference. So here you can see delta net, and now this should look fairly familiar now and help us digest this more easily now that we've incrementally built our way from vanilla linear attention to these more hairy linear attention variants. We can see our householder transition matrix here, generalized householder, but we have this new term. It's a diagonalized matrix of decay factors that are per channel decay factors. Okay, so this is kind of what they are doing, is adding more granular, like per feature decay that is more fine-grained and controllable, so we can get more expressivity in these updates. And what this is doing is basically saying for the original state matrix S of 0, compute the cumulative decay that would have been applied to it by time step R in chunk T, so the rth token in chunk T. And that's one component of our state matrix. And the other component is the same thing we just kind of looked at. For every token from 1 to R, we need to look at the future decay factors, householder matrix with the diagonalized per channel decay factors applied to the actual key value mapping that we want to accumulate into the state matrix, right? Hopefully that makes sense. So they're going to call P of R for this first term here, and then H of R for the second term here, okay? And so now hopefully when we look at this, it doesn't just look like a bunch of craziness. Hopefully we've now built our way up and understood how we got here. I think we can probably move back to, yeah, okay, so here, this is the last slide I'll show from these. So now we know there's this nested for loop here, right? The sum of products, right? So, what the authors are now doing is saying, okay, that's great in theory, like the math makes sense, but as far as computing this in an efficient way on GPUs or TPUs, we need to do better than nested for loop. So they do a couple of transformations to this equation, basically. The first one is called using the WI representation, which is a linear algebra identity that basically states that for a cumulative products of householder matrices, we can actually represent them in this more compact summation here if we know this term W. This is a new vector that we haven't seen yet. But this can be computed through a linear occurrence. And this is where I'm actually going to show Songlin's blog. And we're going to talk through this really quick. I think this is super important to understand. Otherwise, at least for me, it's like hard for me to feel comfortable or confident about my understanding of this if I just like see this totally different equation. I'm just like, sure, like, okay, like I feel like I've not internalized it unless I see the proof of how this maps to that. And don't worry, it's pretty short and it's fairly easy to talk through. So basically, they show a short inductive proof here showing that this product, cumulative product, can be shown as just the identity minus this summation. And they do it by showing, so let me break this into parts. First, P of n, if we look back at the Kimi paper, this is P of n, right? This first term that we're applying, this cumulative product of householder matrices, we are applying to the original state S of 0. This is one thing that we need to prove, right? The next thing that we need to prove if we want to use WI representation is this term, right? This, all the, decayed new updates that we've applied up to time step R in the chunk, okay? So starting with the first one, we look here and they say, okay, first step, does it hold for the base case of n equals 1? And it does, because if this is 1 and this is 1, there's no summation or product. It's just a single time step. And you can clearly just see Wi is equal to beta I times k of I, right? So cool, we did our base case. Next step is to prove it holds for some arbitrary n minus 1, right? And then if it holds for n minus 1, we attempt to prove it for n. So we assume it holds for n minus 1. So here's our equation we start with. This is P of n minus 1, the previous cumulative products we've accumulated up to P of n minus 1, and then our new householder transition matrix, right? And so we can replace, since we're assuming P of n minus 1 the with the thing we're assuming is true, I minus the summation, right? So there it is, up to n minus 1. And then here's our same householder transition for this time step, n. Now, if we use our good old friend FOIL and just multiply it out, I times I, we get identity matrix. I times this term, the summation to n minus 1 is still just that term to n minus 1. I times this term, beta k, k transpose, we just get that term. And then finally, the summation times beta k, k transpose is just the product of those two terms. So now we see that these last two terms, beta k, k transpose, and then this product right here, both have a k transpose in common. We can extract that out. And they also move out the beta n here just outside of the summation. But the point is that this now resembles, if we remember, what we're trying to prove here is that from I to n, or from 1 to n, this w vector times this k transpose is equivalent to this. So this bears a lot of similarity now. We already have I to n minus 1. The only thing we're missing is the nth step. And it does have the k transpose that we would need in the nth step, right? So we now can see this whole term right here is actually the w coefficient that we're looking for. So you can define this as wn, and now you've shown that it is indeed equivalent to I, or the identity minus the summation to n, right? And so now we have this recurrence here because you can see wn to compute it depends on the sum from 1 to n minus 1 of this wt, right? So it's a recurrence that can be used to compute wn. And so or just for w, right? So we have a way to compute the w that we are missing to use this representation, right? And then now, so that's step one. We have now shown this. We've now shown how this term maps to this wi representation, right? And then here it's a little different in the delta net because instead of just beta, they have the diagonalized the k term per feature of the k terms here, but and this is diagonalized cumulative. This gamma here means cumulative up to r. But identity matrix times, you can see how we get the, instead of identity matrix, since we have this new term, you can see how we would get that. So hopefully now, for the first term at least, it makes sense. We say, okay, we see how we got from here to here. Okay, now we have this other one. And don't worry, it's basically the exact same, very similar. We want to show for S, our state, that it can be shown to be representable in this summation form. And basically, we just, again, does it hold for n? Does it hold for 1? Yes, obviously. And then n minus 1, we prove with these short few steps, right? We show, we plug in, previous state times new transition matrix to do the quote-unquote erasure of the key in question here before adding the new key value mapping here. And we plug in, since we're assuming n minus 1 is true, we plug in the summation that we're assuming is true from 1 to n minus 1, and then we still have the rest of our terms from the previous step. And then now we can multiply this out basically, right? Identity times this summation is just that summation. And then this summation times this term is this product here. And then finally we have still our beta vkt. And then now, again, we see the k of t is something both of these terms have in common, and we extract it. And now, once again, we can see that this whole term here we can define as u of n, and that's the coefficient for the nth time step. And now we can express this as just a summation from 1 to n. And we have our equation for how to compute this auxiliary vector u in order to finally represent this as wy representation. So what do we do here? We use this algebraic identity to pack a series of rank 1 updates, meaning that these are, these k v transpose outer product is just a vector. And this is just a vector, right? Basically the erasure and the new information are both contain one rank of information added to the S hidden state, right? And by if these happen to be householder uh, matrices, we have shown how we can represent this in this more compact summation. Now, finally, though, we're not done. So the good thing about this summation is that there is another transform that can be applied to it to now represent it in a quote unquote blocked format that you can use matrix multiplications to implement. And therefore take advantage of your tensor cores and actually utilize the peak achievable, well, uh, utilize a much higher proportion of the peak achievable flops on your hardware to compute this. And here is where I did not get a chance to get a deeper understanding. The blog here does like some analogy mapping it to graph theory, which I skimmed this morning and have not gotten a deeper understanding. I'm wondering if anybody else, perhaps wave function or somebody, could perhaps talk through the UT transform if anybody understands it more deeply than I do. Otherwise, I can do my best, but I think maybe you understand it better than I do.
I can give it a shot if you like.
Sure.
I wasn't really prepared to present,
No, no
but
worries.
yeah, if you bring the paper back up,
Hmm.
and zoom in a bit, essentially, all that's happening here is that they're backing the um, uh, the uh, values from um, equations 3, 4, and 5 for a given chunk into sort of one big matrix. Um, and so I guess I could add the GPT chat where I was going through that with ChatGPT, if that would be interesting.
Yeah, yeah.
Okay. Um, that's it.
Yeah, I tried talking to it as well on this one, and I was getting like inconsistent answers. I still wasn't quite clear, so maybe you can help fill in the
Yeah,
gaps.
sure. Let me just rearrange my windows here a bit. Uh, Um, can you stop sharing and
Yeah.
I'll share? Hmm, when is it? Yep. Okay. So it's somewhere in here. Uh, let's see. This
Wow, 12
equation is
minutes
16.
of thinking. Jeez.
Yeah, it was in pro mode. It can't, ChatGPT can't really be used for this kind of stuff, unless it's in pro mode. Um,
Got it.
like I was trying to use thinking to save some time, but it kept giving me garbage. So
Hmm.
yeah, don't do that. Um, Okay, and let me just bring up the paper as well, so I can flip between them.
Is there a screen share happening? Because I can't really see anything.
Yeah, go to the voice channel meeting and click it on the left bar of Discord. Can you see it?
It says the stream has ended.
Oh, so exit. That's probably mine. Exit that, and then just click the meeting on the left in
Oh,
the voice channel, and then click on his. Uh,
okay, wait, I see. Oh, okay, cool, thanks.
mhm.
Okay, right equations 6 and 7, but we want. Oh yeah, 6 and 7 are exactly what we want. Okay, yeah. So because it screwed up the LaTeX, um, we're looking at these two equations for the UT transform.
Mhm.
Um, So, just a little bit of notation. This is a strict lower triangular matrix. So, what's inside here is not actually uh, lower triangular. Um, It's like you just take the everything below the diagonal basically. Um, and so what we have here is just a lower triangular matrix for the whole thing. Um, so the fact that it's taking this inverse is not as bad as it looks because to invert a strict triangular matrix, you can just use Gaussian elimination. Um, and so the idea is that these recurrences here are expressed in these two equations here. So we have this sort of common structure to this in that we have this sort of Gram-Schmidt orthogonalization type structure in both cases, same KIs, same decay, diagonalized cumulative decay measures. And so all of that is actually already described in here. So then the question is, like, why would this funny inverse uh, allow us to compute U and C just with these simple matrices? Also, just to uh, establish the context here, the reason why we want to do this is that this is a matrix multiplication here, large matrix multiplication. So, we can just blat that at our tensor cores and it'll do it. Whereas what we have up here are these sequential recurrences, which, would be relatively hard to parallelize. So that's the reason why we're doing this. Okay, so keep this equation in mind. This equation is, wait, where did it go? Here we go. Anyway, yeah, so this equation is this big red blob here, which it failed to convert to readable human text. Okay, so just as a matter of notation, they're going to call this. So this is basically um, a weighted inner product, and what we're weighting by here is the decay rate between these two keys. So between key I and key R, we're going to have these multiple forget parameters. Call them gamma J, and this is basically the products of gamma I through gamma R. Okay, so basically what we're doing is we're stacking everything into these matrices. So K is just each row is the keys, similar for V, W, and U. So these are the K and V here are just the keys and values, similar to what you have in a transformer. And then U and W are these funny Gram-Schmidt type expressions that we're getting for the more efficient householder representation. And then beta is basically the get rate, the learning rate, I guess. So you have a kind of like you can make this a data dependent learning rate. I'm pretty sure this is the learning rate, but we could go back and check that. And then finally, this gamma 1 to C for each row has basically the combined uh, forget rates uh, for step R. So this gamma R here is basically the product of all of the forget rates up to position R. Okay, so that's the notation. Before we move on to the actual derivation, Does anyone have any questions about the notation? Or is there anything that's unclear to anyone?
I think it makes sense. I think one question I had we could just double check
Okay.
on is the difference between the beta, because you said it's like you think it's like the learning rate. Is it um because they have beta and they have these diagonal like gammas in the paper. Is
Hmm.
one, I think my understanding is the diagonal gammas the per channel decay factors, but the beta is when you say learning rate, I guess what do you mean? Is that like just the global um like generalized householder coefficient that we're applying to the KK transpose? And then the gammas are
It's a
per
term which,
channel?
yeah, it's a term which comes more from this delta net formulation, where like
Mm-hmm.
you treat them as fast weights, and then at each time step you're sort of trying to do SGD on this loss. And so like when you do that, um, beta T actually uh, forms your learning rate essentially.
Mm-hmm.
Does that make sense?
Yeah, my confusion is
It is a forget. It's a kind of a forget mechanism as well. Like
yeah.
when you go to the householder framework, that is a forget mechanism as well. But it's more on the level of overall keys, whereas the gammas are more on the level of where do
per
they define the
per
gamma?
channel, right? Or per
Yeah, let's
feature,
see
sort
if
of.
I can find.
Yeah, because my like confusion reading this paper was why do we need both? Like, why isn't just the per channel forgetting gate good enough? Um, like, why do we also need
Hmm.
beta?
Yeah, that's an interesting question. So if we get rid of beta, or let's say we fix beta, essentially what we would be doing is fixing that learning rate in the fast weight formulation, which might make sense, I suppose. But like it makes sense to make that data dependent as well, I think.
Mm.
Um,
So it's kind of like it would be like a householder transform matrix where we are essentially flattening the vector instead of reflecting it. If it's just the beta is one, basically, if we remove beta, it's like beta
yeah,
is one. So you would be like unconditionally flattening and then trying to apply a per channel decay, the diagonalized gamma here. So I guess really it would be
mhm,
pointless, sort of like if you flatten it out, or all parallel vectors or all components that are parallel to the KKT target of the householder, and then you try to apply some diagonalized per channel decay, there's nothing left to decay, right? So I guess the beta needs to be some learnable value.
I think it's highly beneficial for it to be a learnable value because it's it's basically playing a similar role here as forget gates
Hmm.
in RNN.
So can
So yeah, I think that's highly desirable.
can we think of it as the beta is like scaling down all parallel components to the k vector in question in the transition in the S matrix, and then the diagonalize is doing a more granular like per channel scaling or decay
But
on that scaled vector. Is
yeah,
that
I think that's a good way of thinking about it. Yeah,
okay? Okay,
totally.
this makes sense to me then.
Yeah, yeah. So yeah, that's exactly what you can see here actually. That like this diagonal alpha I here is basically going to be scaling each row in your state matrix, and each row of the state matrix basically corresponds to one of the channels
Hmm.
um, in your keys and values. And keys,
Cool.
get any keys. Yeah. Okay. Um, yeah. All right. So just to go through this in a little more detail here, what we have here, remember the rth row of this is going to be the per channel decays uh, up to time step r. And then we're doing uh, element-wise multiplication of that with our stacked keys here. And then we're basically doing a dot product between our stacked keys with themselves here. And here we're doing element-wise division. And the reason why we do that here is so at step R, these are basically gamma 1 times gamma 2 up to gamma R. And similarly here, so when we take this product of K with the transpose of itself with these multiplications in here, these factors and these factors are going to cancel out. So remember, this only applies to the lower triangular part. It's the only part we care about. So we're going to get a larger value here and a smaller value here. And so we're going to get gamma 1 times blah, blah, blah up to gamma r. Well, let's say we're looking at I and j here, where I is larger than j. So, sorry, where j is larger than, yeah, where j is larger than I, sorry. So we're going to get this gamma I to r term out of here, because this is gamma I times gamma I plus 1 up to gamma r. And this divided by this at I and j are basically going to give you gamma 1 up to gamma j divided by gamma 1 up to gamma I. So we'll just get gamma I up to gamma j. So that's what's going on here. And then so let's actually start going through the derivation of this now.
Oh wait, can we pause for 1 second?
Yeah, sure.
On what you were talking about, so in effect, is that inner expression you were just showing, is this to achieve the
Mhm.
relative cumulative decay between steps I and J at the bot or in the
Yes.
in the middle there with the sorry, what is that? Is it row or how do you say that Greek? Below in the
This one
red.
here.
Just the
Oh,
M
this.
matrix, the M matrix, yeah, because you said they cancel the one there, and then we're doing element wise, and then we're also dividing, and then the transpose. Um,
Mm-hmm.
I just wasn't clear on the intuition of what this is accomplishing. You said is it the relative decay, cumulative decay between steps I and J applied to
Yes.
K transpose?
Yes. So remember, we're using this to get our U's and W's
Yeah.
in this stacked format.
Mm-hmm.
So both of those have this sort of decay weighted dot product of
Mm-hmm.
the key vectors. Um, and so these diagonals only go from gamma I up to gamma R. So we need a way of ensuring that. And if you work this out, essentially what the fact that you're multiplying here and dividing here and taking the strict lower triangular matrix here means that you're going to get exactly these.
Hmm. Okay.
Yeah. Okay, let's go through the derivation. So this is so ChatGPT screws up some of the notation here, but we can correct for that. Okay, so we've got this term here is just this term here. So we're calling that. Oh, that's why that happened. Okay. Yeah. So we're just calling that D for the time being. And then these G's here are just these sort of Gram-Schmidt type terms in U and W. So that's G. So the rth row and ith column is just dot product between I and R with the decay between those two time steps. Okay.
Okay.
So now what we're going to do is we're going to write these recurrence relations up here using this matrix. So that's what I'm saying when like really this is a way of getting this sequential relationship sorted out just in these two matrix multiplications here, which we can just bladder to the GPU. Okay, so we've got WR is equal to beta R times DR minus the sum of the GRIWIs here. Let's just check that that actually is what we want. So we've got the gamma R times KR for DR here. I diagonals gamma R times KR. And then we've got this this dot product here. Let's have a look at that. Yeah, so we take the beta out the front here, and that is exactly our DR. And this is, let me just check here. Yeah, this is exactly this term here. Whoops. All right, so the order is reversed, but we've got the earlier WIs here, and then we've got the this is just the GRIs that we were talking about before. Does that make sense?
I think so. Could you go back? Yeah, so,
Okay.
yeah.
Okay. So now we've got this form here. Great. So now we can just stack these rows up. So the B here is just a diagonal with the beta R's on the on the diagonals. Similarly for D, and then this is an actual product here.
Could you scroll up for
Okay.
1 second just to see
Yep.
how to the um, okay. And D, could you go back up to D? Sorry.
Yep.
D was this times K. Okay.
Okay. So now we've got this nice matrix expression for the stacked W's. And basically what we do now is we just solve that for W. So yeah, just distribute the B's over. So we get this. Then take all the W terms together, factor out the W, and we get this. And then we just take the inverse here. And remember, this is lower triangular. So the inverse is inexpensive to compute using Gaussian elimination. So finally, we get W in this format, and that is exactly this. Okay,
I see.
and
So,
it's similar for you. I don't think it's really necessary to go through it for you as well. You can see
mhm.
that we have a very similar structure here. Whoops. Let me get back to that. Here it is. Yeah. So then you can do the same thing and actually express the final state using just this matrix multiplication here. Now that we've got these stacked U's and W's here, we just do one matmul here, and then one matmul here. This one's easy, and then we've got a bunch of additions. So yeah, we can go through 8 as well. if people are interested in that. Um, like I think this is probably what they actually use.
Yeah. Wait, if you go down a little bit, I think they have one more, right?
Mhm. Yeah, they do.
Um,
Yep.
yeah. Oh, this is for the
Yeah.
output
So
projection. Yeah.
yeah, yeah.
Got it.
It's similar. I have not actually fully understood this one, although I got ChatGPT to produce the um, derivation, so we could go through that if people are
Mhm.
interested.
I think it would be helpful.
But
Could you
yeah,
share the response that you got from GPT Pro?
yeah,
Is
sure.
there like a shareable
Hmm.
link? Yeah, that'd be awesome to go through and digest later. Um,
Yeah,
yeah,
let
I
me
feel
check
better
whether
about
I've
it.
asked
I feel
any
better about it
dumb
now than I
questions.
did before. Yeah.
Yeah. Uh,
So this,
yeah. Okay. Yeah, this should be fine to share.
yeah, I was just wondering, so for this, when I was researching WY representation in UT transformation, it seems like the context in which this would have been introduced to the authors. Basically, like I did not encounter this anytime in school or in any other ML papers I've read. It seems like it's sort of like numerical linear algebra techniques for high performance computing, like when you want to be able to represent things in forms that are more, friendly to computers, parallel processors, basically. Um, is that the case? Like, have you seen this before, basically? And if so, like, where have you seen it?
I've seen similar things for I think in the RWKV7 paper.
Mm-hmm.
Um, but yeah, I'd never heard it called the UT transform before.
Interesting. Yeah, I was like wondering where the authors learned about this. Like this never would have occurred to me in like a million years
Mm.
I guess it's the kind of thing you either know or you don't. Like you're familiar with this identity that's been proven before and
Uh,
you can use it. I don't know.
I don't think so.
You don't think so?
No, I think this would naturally come out of trying to optimize these sequential relationships, and I could be wrong, of course, but like,
Mm-hmm.
this is very similar to Gaussian elimination in the first place. Um, so like, yeah, but the proof of the pudding would be in this 46 link, I suppose. Uh, let's see, can I get that?
Isn't, sorry for a dumb question, but isn't Gaussian elimination like what we do to get to like reduce row echelon form? We like go row by row and try to like eliminate and get like a triangular matrix.
Yeah, yes, but if you have if you have a lower triangular matrix, then you can just invert that by what amounts to Gaussian elimination as well. Uh, let me just find that. Uh, let's see, this should have it. Yeah, so there ought to be a better example than this. Um, someone must have animated this, but I'm not sure where it is. Anyway, I would suggest just doing that as an exercise. Um, uh, take a two by two or a three by three lower triangular matrix and figure out what you need to do in order to invert it.
Mm-hmm.
Um, just by solving the equation. Um, a times a inverse is equal to I, and you'll find it all drops out really easily.
Okay. Yeah, it just sounds like some like iterative row-wise Gaussian elimination sounds like something that would be slow on a GPU. Like it does not sound like a highly parallelizable mammal type of operation. But I guess it's sufficiently fast for this purpose.
That's a really good point. Yeah, yeah. Essentially, you're just moving the uh, this sequential calculation into converting.
Hmm.
And yeah, so yeah, I would be interested in seeing the code or the way they do have code for this actually in here, don't they?
Hmm.
Let's see, I have not looked closely at it
I
though,
think,
so
um, yeah, I haven't looked at it either.
see where they do
Yeah,
see if we can discern where they actually calculate that. And so A is what we're looking for. Okay, this is it here. Where's GC? Well, that's the gammas, I guess, right?
cum sum.
Uh, A times.
Why exponentiating? Oh, is it because it's like a cumulative?
I guess,
Oh, well,
yeah, I guess they keep those in log representation. Okay, so A is the M. Um, but where are they doing the inverse? That's the bizarre thing from my perspective.
yeah, they have an upper triangular mask.
Maybe the inverse is being done here. I don't really understand this code. Um,
Hmm.
and it is exactly the kind of thing that you need to do in order to convert a lower triangular matrix. Um, so I guess this is the inverse, like the, basically doing the operations for the inverse before they add in the ones on the diagonal.
Hmm.
Um, but yeah, this you raise a good point. They're still doing this sequential operation here, and why that would be faster than just working out U and W directly is not completely clear to me at this point.
I wonder if, because this is just like pseudocode, right? I'm curious if there's some algorithm to parallelize the sequential, like iterative Gaussian elimination, because there's like things that seem like, if you're familiar with the parallel scan algorithm from like CUDA programming, there's things that would seem to have like a hard sequential dependency that there are parallel algorithms to solve in like log n. Like, so maybe there's some clever way of doing Gaussian elimination faster than just straight up iteratively. I'm just wildly speculating though. I don't know.
Yeah, it doesn't look like they provide code, like actual source code for this paper.
Hmm,
So
that's annoying.
if people know where there is where the implementation is, that would be great. Then we could look at the actual code they use and uh, see if they see if they can use some kind of CUDA magic for that.
Yeah. Okay.
It does
Cool.
seem like
Well,
a limitation, though, doesn't it?
yeah,
Hmm.
yeah. Because the whole point of the UT transform was to avoid the sequential summation to compute the W and the U, right? To make it more
That was what
GPU
I thought.
friendly.
Yeah.
Yeah. It might just be maybe the summation to do the Gaussian elimination, or not summation, but like iterations for it is very small. It's like number of rows in the matrix, right? I don't know. It's still kind of large, so I'm not sure. Um, yeah.
Yeah, it's like, this is for a given chunk, and so like you're you're still going to be doing this for every single token.
Hmm. Yeah.
Yeah, it's interesting. Might be worth writing the authors to ask. Yeah, but without
Yeah.
the code, it's hard to say how that works.
Hmm. Yeah, I'm
Maybe
curious.
the idea is that once you've got these guys, like this part has to be done sequentially, but then once you've got those, oh, that might be what it is. Okay, yeah. So we still have to do some sequential work to get these. This almost seems like gilding a lily. This M thing almost seems like gilding a lily. Um,
The M almost seems like what?
so no, it's a nice abstraction, I guess. Gilding the lily, like an unnecessary embellishment.
Oh, okay.
Like
Little
yeah, I think
idioms.
yeah. Sorry.
I like it.
um, yeah. Uh, I can't at the moment. I can't see why this would be significantly slower than this. But this I can see. Like this part makes sense to me. Because like once you've got all of those stacked, you really can't like these are significant savings.
Yeah, yeah,
Otherwise, yeah.
yeah. Okay. Well, thanks for walking us all through the UT transform. I feel like I made some progress in my understanding. Um, yeah, I learned a lot from this. I never have dived into linear attention before, so hopefully everybody else also um, got something out of it today. I gotta run now. I'm starving. Gotta make lunch. But yeah, appreciate everybody joining. Any other last minute comments or questions? Cool. All right. Well, big thanks again to our good friend Wave Function for providing some insight into the UT transform, and hopefully everybody got something out of this today. So yeah, see everybody next time.
Yep. Bye everyone. Thanks.